Welcome. Thank you, Professor Lowe, for giving me this opportunity. Here is my solution to the problem. How many five-digit integers exist where the digits are non-increasing from left to right? Oh, shucks, this problem is super tricky. There are 90,000 integers. There's no way we can count all of them. But let's see if we can break the numbers down into groups. Let's start off with an easy one. When all the numbers are the same. Only 9 numbers are like this because of the digits 1 through 9. Now let's investigate when all the numbers are different. What's interesting with this case is that for every group of 5 digits we choose, there's only one arrangement and only one number that satisfies this non-increasing condition. And this seems to be true for even repeating digits. If you look at the examples here, even though 78987 doesn't satisfy the property, we could have arranged it like 98877, and that would have worked. To find all the numbers like A, B, C, D, E, we can do 10 choose 5, which is 252. If you forget how to find the number of ways you can choose R objects from n distinct objects, here is the formula for n choose R. Okay, now we just got to do this for the rest of the cases. For A, B, C, D, when only one number is doubled, it's 10 choose 4 times another 4 to choose which of the numbers we should double, and that equals 840. For A, B, B, C, it's 10 choose 3 numbers, and then from those 3 numbers, we'll choose 2 more to pick which 2 numbers will be doubled. And when you multiply those, you get 360. For A, B, C, it's 10 choose 3 numbers times 3 choose 1 number to be doubled, and that equals 360. For A, B, B, it's 10 choose 2 numbers times 2, because we need to choose one number to triple, and that will make the other number automatically doubled. Finally, our last case is A, and to find the number of numbers that are like this, it's 10 choose 2, picking our 2 numbers again, times 2 to pick which of the 2 numbers should be quadrupled. Now we add everything up, so 9 plus 252 plus 840 plus 360 plus 360 plus 90 equals 2001. Wow, that was a lot. Okay, to be honest, that was a very complicated problem that we solved with case word counting. But there were so many ways we could have messed up. We could have forgotten one of these cases, or we could have easily messed up the calculation, and that would lead us to get the wrong answer.
Oh, hell no, man. What the fuck?
As Richard Russick always says, we can double check our answer by solving the problem in a different way. If we get the same answer, then we have the correct answer. Okay, I want to bring us back to the idea that as long as we choose our 5 numbers, even if they're repeating, we can only get one good number using those 5 digits. So to find a clever way to generate all of these 5 digits, let's imagine a game. Okay, so we have 5 balls. Here are our 5 balls right here, and we have 10 buckets, each labeled for a possible digit. Now, in this game, we're going to pretend to toss our balls into these buckets. Wherever these balls land, they tell us the digits that we will use in our number. And as we can see here, 1 ball landed in 0, 2 and 3, 1 and 5, and 1 and 9. And the only number that has 1 9, 1 5, 2 3s, and 1 0 that also satisfies this condition is 95,330. Now, this type of problem where identical objects are distributed across distinct containers has a special formula called stars and bars. It works by representing the n objects as stars and k-1 bars to separate and distinguish between the different categories. In this case, we'd have 5 stars for our 5 balls and 9 bars for our 10 buckets. Now, we only need to count the number of arrangements of these stars and bars because each arrangement of these stars and bars leads us to one number. And we can do that by saying every star to the left of all the bars tells us how many zeros there are. All the stars between the first and the second bar tell us how many ones there are. Between the second and the third tell us how many twos there are, and we can go on all the way up to 9. The number of arrangements can be calculated by doing 14 choose 5 because we essentially have 14 spots and we need to choose 5 of them to be stars because that will make the rest of them automatically bars. So for example, in this arrangement, we've chosen the stars to be at 1, 4, 5, 7, and 11. And we fill the rest with bars. That tells us there's 1, 0, 2 twos, 1, 3, and 1, 6. That's like the same way as if we were to toss our 5 balls and one of the balls landed in 0, 2 and 2, 1 and 3, and 1 and 6. And the only number that works involving these 5 digits is 63220. Computing 14 choose 5 gets us 2002, but we have to subtract 1 for the case when all the stars are to the left of all the bars. That would equal 00000, and that's not a 5-digit number. So 2002 minus 1 equals 2001. This strategy is known as constructive counting because we've systematically built every possible case to get our answer. And there you have it. 2001 is the number we got with case root counting and constructive counting, so we can be pretty confident that we're correct. Thank you.